To start, let's discuss how Newton's three laws are involved in It's a Small World. To review, Newton's first law, an object at rest tends to stay at rest. This is inertia. An object in motion tends to stay in motion. This is momentum. Newton's second law is more of a formula than a law. The net force equals the product of an object's mass and acceleration. The net force is how much more or less an object is being pushed or pulled. Newton's third law, for every action there's an equal but opposite reaction. This law states that forces come in pairs. To put it all together, we can analyze and understand how an It's a Small World boat works. A boat on It's a Small World moves due to the current in the water. The water pushes on the back of the boat, so the boat pushes back on the water with an equal but opposite force. As the boat travels along its track at a constant velocity, it does not accelerate because it does not speed up or slow down. Its velocity does not change. The boat is an object in motion, so it tends to stay in motion. This is because the forces acting on it are balanced. When the current pushes on the boat more than the water drags on it, it can cause the forces to become unbalanced. This outside unbalanced force causes the boat to accelerate due to the net force applied by the current. A 1,880 kilogram It's a Small World boat is traveling at a constant velocity. The current applies 5 newtons of force, and the water applies drag, or F subdrag, against the boat's motion. Let's start by looking at the given information. I know the boat's mass, and I know how much the current is pushing on it. There are some subtle hints. The words constant velocity implies not only does the boat start and end at the same speed or velocity, but it has balanced forces and an acceleration of 0. Before we analyze the forces acting on the boat, let's look at all the forces that we know. Gravitational forces are caused by the pull between the object and the Earth. Every object on or near Earth has a gravitational force. We calculate it by multiplying 9.8, Earth's gravitational force constant, times the object's mass. A normal force is caused by any surface and creates a force that is perpendicular to the surface. An applied force is any general push or pull, not caused by gravity, a surface, or a rope, like a tension force. Tension forces are really just a specific version of applied forces. Friction is caused by two surfaces rubbing against each other. If the object is moving while experiencing friction, we have kinetic friction. If the object is stopped due to friction, we have static friction. Friction always acts opposite to the object's motion. When we're in a fluid like water or air, sometimes we call friction air resistance or drag, especially when we're dealing with buoyancy forces. Let's analyze the forces acting on the boat. I know that gravity's acting on it because gravity's always acting on objects. So I can calculate that gravity using this formula. I know the object's mass, 9.8 times 1,880, gives me 18,424 newtons. Gravity always pulls straight down or towards the center of the Earth. That's my gravitational force, and I know it's 18,424 newtons. Because the boat's not flying into the air or sinking into the water, its buoyancy forces are balanced, so its vertical forces are balanced, so they're equal. I know that it's moving forward because the current is applying a force of 5 newtons. Not only do I know that there is drag, which acts like friction when water's involved, but the boat is moving at a constant velocity. So not only is there a force pulling back on the boat, but it's equal to the force pushing forward. Balanced forces in all directions prove that the boat is moving at a constant velocity. Now that we know why it's moving at a constant velocity, let's analyze what happens when it moves at a constant velocity. Let's find our given piece of information. The boat travels 9.45 meters. That's my distance. Meters is the unit for distance in 15 seconds at a constant velocity. I'm trying to find my initial velocity. I need 3 given pieces of information. I've only been given 2. Whenever I'm missing a value, look for hints. In this case, I've been told it's constant velocity. When an object moves at a constant velocity, it has an acceleration of 0 because its forces are balanced. I was given distance, I was given time, I can assume an acceleration of 0. I'm looking for initial velocity, so my final velocity is not included. Let's take a look at how we use our kinematic equations before we calculate the initial velocity. Always ask yourself, what variable was not included? In this case, final velocity was not included. I was given 2. I assumed a third because constant velocity has an acceleration of 0. And then I'm looking for initial velocity. Final velocity is not included. So I go down to final velocity. I'm solving for initial velocity. There's the formula. Unless I want to use the formula at the top and challenge myself to solve. Now that we're reviewed, let's do the work. This is the information that we pulled from the word problem. We read the word problem, analyzed it for given information, and then had to make some assumptions. Now we know the right formula because we used our kinematic equation sheet. At this point, it's a matter of plugging and chugging. I replace every variable in my formula with the given information from my list of given information. Order of operations says that anything times 0, so 1/2 times 0 times 15, that can go away. And I'm left with just 9.45 divided by 15. There's my initial velocity. Now, interestingly enough, even though the final velocity is not included because it's moving at a constant velocity, its initial velocity is 0.63. So its final velocity is 0.63 meters per second. Let's look at what happens when the forces become unbalanced. We have the same boat because we have the same mass. But now the current is applying 7.5 newtons forward while there's only 5 newtons of drag pulling back on the boat. Let's analyze what we know about the net force to understand acceleration. We can explain the net force a couple different ways. There's Newton's second law, which states the net force equals the product of mass and acceleration. So an object's mass times its acceleration equals its net force. This net force equals how much more or less a force is pulling on the object. It's like tug of war. The net force is the winning team. We can think of the net force as the difference between two forces acting on an object. So if the current is pushing on the boat with 10 newtons and the drag is pulling back with only 5, then my net force is 5 newtons. 10 minus 5 equals 5. You subtract opposing forces. The net force only exists when forces are unbalanced. If forces are balanced, there would be no net force. 10 minus 10 equals 0. Let's do the work. Let's draw our force diagram. We know that gravity's there. It's the same boat, so we have the same gravitational force. Generally speaking, unless the object is accelerating up or accelerating down, our vertical forces are going to be balanced. Because the boat's floating, forces are balanced. We have an applied force from the current of 7.5 newtons. The water is still pulling back with 5 newtons of drag. The difference between our two forces, so our applied minus our drag force, because our horizontal forces are unbalanced, equals 7.5 minus 5, so I get a net force of 2.5 newtons. Based on the forces acting on the boat and the mass of the boat itself, I can find its acceleration. The net force is either the difference with forces or it's Newton's second law. The product of mass and acceleration. So in this case, I know my net force is 2.5. I know my mass is 1,880 kilograms, so I can solve my acceleration. My variable is A. What's happening to A? I'm multiplying, so I'm going to divide both sides by 1,880. My acceleration, very small, but safe for a kiddie ride. My acceleration is positive because I'm moving forward and speeding up. I know I'm accelerating and speeding up forward because my net force is pulling forward. The applied force is pushing, or the current is pushing with 2.5 newtons more than the water or drag is pulling back. The last boat from the last problem speeds up from an initial velocity of 0.63 meters per second. So we know its initial velocity, how fast it's moving at the beginning of this motion we're about to analyze. We're going to use the acceleration that we found in the last problem. How fast will the boat be moving after 12 seconds? This problem gives me my initial velocity, it gives me my time, and if I look back at my last problem, I can find my acceleration. Be careful if a problem references another problem. Not all of your information is always in the word problem at hand. We were given our initial velocity and our time. We already knew our acceleration. We're trying to solve for our final velocity. So the variable that's not included is distance. We weren't given it and we're not looking for it. I'm trying to find final velocity, so there's my formula. Let's do the work. Here's all our given information. We were either given it in our word problem or had to look back at the previous problem to find our acceleration. I know all of those givens and I follow the order of operations. I take care of my multiplication first, I take care of my addition, and there's my final velocity. The answer seems reasonable because we had a small acceleration, so we had a small change in initial and final velocities. This problem talks about more than one object, so we're going to be dealing with momentum. Boat number one has a mass of 1,880 kilograms and is traveling at a velocity of 1.33 meters per second. I know its mass and velocity, so I can find this boat's momentum. It bumps into boat number two, which has a mass of 1,810 kilograms and is stopped or has a velocity of 0 meters per second. I can find this boat's momentum. After the collision, boat number one bounces off backwards at a velocity of 0.5 meters per second. If it's backwards, the velocity has to be negative. It won't always flat out tell you a velocity of negative 0.5 meters per second. Sometimes we need to visualize these things. So think about it. Boat one is moving forward. Boat two is stopped. Boat one bounces off backwards. Boat two travels forwards. Let's do a little background knowledge. What do we know about conservation of momentum? We know that momentum, with the exception of impulse, involves only one formula. P equals m times v. The mass times velocity of an object equals its momentum. When we're dealing with two objects colliding, we have to ask ourselves, is it elastic or inelastic? Does it start as two objects, bounce, and end as two objects? Or does it start as two objects and end connected as one object? This is elastic. These objects bounce off. So we start with two, end with two. It's almost like a game of chess. You're playing step by step. You start by filling in the given information. I know the mass of my boat one and boat two. The masses don't change, so I know the masses of both boats after as well. I was given the velocity of boat one and the velocity of boat two, so I know that information. This simple formula requires two variables, mass and velocity. I know the mass and velocity for both boats. Mass times velocity of boat 1 gives me the momentum of boat 1. Mass times velocity of boat 2 gives me the momentum of boat 2. If I add their momentums, I can get the total momentum. The total momentum is what connects you from before to after. Conservation of momentum states, or the law of conservation of momentum states, that the total momentum before a collision equals the total momentum after a collision. In the case of this problem, I was given one of my boat's velocities. If I know a mass and velocity, I can find a momentum. I only need two variables. So I'd be able to find that boat's momentum after the collision. Total momentum is the sum of the two individual momentums. The shortcut, if I know the total momentum and I know one object's momentum, I take the total momentum minus the individual momentum of boat number 2 in this case. That would help me find this boat's momentum. Now that I have two variables, I can solve. I would plug in the mass of boat 1 after the collision and the momentum of boat 1 after the collision. And then I would solve for its velocity. Let's apply that and do the work. I know some given information about these two boats. I know their masses before and after. I know boat 1's velocity and boat 2's velocity. I only know boat 1's velocity after the collision. These are the 7 given pieces of information that I know. Once I have my given information in, I need to start looking for ways to use my formula, P equals M times V. I see a mass and velocity, so I'm going to multiply boat 1's mass and velocity. There's boat 1's momentum. Boat 2's mass and velocity, there's boat 2's momentum. We also know that if an object's not moving, it does not have momentum, it just has inertia. To find the total momentum before the collision, I add those two up. 2,500.4 plus 0 equals 2,500.4 kilogram meters per second. The momentum, total momentum before equals total momentum after. Whenever I get stuck, I try to find that way to use that formula. I know boat 1's momentum, mass after, and its velocity after, so I can find its momentum after. There's a shortcut. If I have the total momentum and one of the individual momentums, I subtract them. Or I can treat it like a one-step equation. Momentum for boat 1 plus momentum for boat 2 equals the total momentum. Either way, I'm subtracting 2,500.4 minus negative 940. I get 3,440.4 kilograms meters per second. That is boat 2's momentum. Now that I have two of the three variables, I plug it into my formula. I know boat 2's momentum. I know its mass. I can solve for its velocity. Velocity is being multiplied by 1,810, so I divide both sides by 1,810. There is the velocity of boat 2 as it moves forward. This confirms what we visualized when we read the problem. I visualized the boat going forward, and here we have a positive velocity. This seems like a reasonable answer. Going along with momentum comes impulse. An 1880 kilogram boat comes to a stop in 1.1 seconds at the end of the ride from an initial velocity of 1.2 meters per second. I have a lot of given information here. I have time, I have an initial velocity, and I have mass. I also see that the boat comes to a stop. Sometimes the word stop or at rest is missed. This is our final velocity of 0. There are three ways to calculate the change in momentum or impulse of an object. An impulse happens when an object changes momentum. So you can find it by subtracting its final momentum minus its initial momentum. If you know the object's mass and its final and initial velocity, like we do in this case, you can solve for the impulse using this formula. If you know the force that acted on the object to cause the impulse and how long the force acted on the object, you can solve for its impulse this way. These formulas can be used to solve for the impulse, or if you know the impulse, it can be used to solve for any of the other variables. For example, if I know my impulse and I know how long or how much time the force acted on the object, in this case to slow the boat down, I can solve for how much force acted on the boat. This isn't a kinematic problem, but since there's a lot of given information, I want to organize my information the same way. I know my initial and final velocity, I'm coming to a stop. I know how long that stop takes, and I know the boat's mass. Because I know both velocities and mass, I can find my impulse using this formula. I'm going to plug in the information I know. 0 minus 1.2, using the order of operations because it's in parentheses, it's going to give me negative 1.2. Be careful there. In this case, I get negative impulse, which is okay because when I go to look at my forces acting on my boat, I can plug in my impulse. I know that the stop took 1.1 seconds. So this is actually telling me that it's negative 2050.91 newtons. Now you can write it as positive. The negative is telling us that it's acting against the boat. If the boat is trying to move forward, this force of 2050.91 newtons acts backwards. In this case, there's a treadmill that runs backwards under the boat to stop it.